This lesson is about electrochemical and electrolytic cells. What we will do in this lesson is we will compare the general nature of electrochemical cells and electrolytic cells, note the difference between the two, write reactions at the anode and cathode for both the electrochemical and electrolytic cells and compare them, explain the electrolysis of molten NaCl, aqueous NaCl, and aqueous potassium nitrate. Predict the change in pH on the oxidation and reduction of water at the different electrodes. Calculate the mass of reactants produced at the cathode and anode using Faradays Laws. Those are some of the things that we will be discussing in today's lesson. Let's take a look at the different kinds of cells that we are talking about today. The first one is electrochemical cell. It's also called the galvanic cell or the voltaic cell. And the second one is electrolytic cell, which we have not discussed yet. Let's see some of the properties of an electrochemical cell. In an electrochemical cell, chemical energy is converted to electrical energy. There are two separate compartments, the anodic compartment and the cathodic compartment, where we have the oxidation half reaction and reduction half reaction. The anode in an electrochemical cell is at a negative potential and the reaction at the anode is oxidation. The cathode is at a positive potential and the reaction is reduction. E cell for an electrochemical cell is always positive, therefore it's spontaneous. From thermodynamics, we know delta G is negative for a spontaneous reaction. Delta G is equal to delta H minus T delta S. And for spontaneous reaction, delta G should be negative. So all these are true for the electrochemical cells. So we're going to compare it to the electrolytic cell and see what the differences are. The electrolytic cell, electrical energy has to be used to bring about a chemical reaction, which is the opposite of an electrochemical cell. The reaction takes place in a single compartment where we have two inert electrodes. In this case, we're going to use platinum electrodes, and we will use a battery to pass electrical current into the solution contained in the electrolytic cell. The anode is at a positive potential, which is different from the electrochemical cell, but the reaction is still oxidation. The cathode is at a negative potential, and the reaction is reduction. Since the reaction does not take place by itself, we have to supply energy for the reaction to take place. It's a non-spontaneous reaction. If you calculate E cell for the electrolytic cell, it's going to be negative, which means the reaction will not take place. It's non-spontaneous, and therefore delta G will also be positive. So those are the properties of an electrolytic cell. So we know the difference between the two. Next, we will look at how the whole construction works and what are some of the uses of the electrolytic cell. The first thing that we're going to do is we're going to study the electrolysis of molten NaCl. When I say molten NaCl, what I mean is sodium chloride solid is taken and it is heated to a very high temperature, and now you have a liquid which contains sodium ions and chloride ions. And we will put two electrodes in it, platinum electrodes, and pass an electrical current into the molten sodium chloride. And then we will observe the reaction that are taking place at the anode and the cathode. The electrolysis here is a non-spontaneous reaction. Electrical energy is provided to bring about non-spontaneous reaction. The anode is at a positive potential and oxidation occurs at this electrode. And usually non-metals are produced here. The cathode is at a negative potential and reduction occurs at this electrode. Metals and hydrogen are produced at this electrode. The electrodes used are called inert electrodes, and we are going to use platinum in this case. Here is a representation of an electrolytic cell. We have a single compartment. We have two electrodes. The two electrodes are connected to the positive and the negative terminal of a battery. The positive terminal is the anode and the negative terminal is the cathode. And we have molten sodium chloride inside this container. So let's label it. The anode, which is connected to the positive terminal. The cathode, which is connected to the negative terminal. The reaction at the anode is going to be oxidation. The reaction at the cathode is going to be reduction. Let's write reactions. The reduction would mean the sodium ions that are present in the molten sodium chloride will take an electron from the electrode that is attached to the negative electrode of the battery, which is the cathode, and it gets reduced. Reduction, as you already know, is gaining of electrons. So Na positive plus electron gives you Na is a reduction reaction. Cl, on the other hand, the chloride ion, is capable of being attracted to the positive electrode because it is negatively charged. It gives up its electron and changes into a chlorine atom. Chlorine atom cannot exist by itself. It forms a diatomic chlorine molecule. So two chloride ions will approach the positive electrode, give up its electrons, and change into Cl2 gas. Electrons being used to reduce the sodium ions. At the same time, the chloride gives up its electrons and changes into chlorine gas. So at the cathode, you will get solid sodium atoms, and at the anode, you would get chlorine gas. The oxidation half reaction and reduction half reaction are represented here. So that's how an electrolytic cell works, and the products obtained at the respective electrodes are sodium and chlorine gas. So let's summarize. Electrolysis of molten sodium chloride, since there are only sodium ions and chloride ions. At the cathode, reduction takes place, so produces sodium metal. Na positive plus electron gives you Na. Likewise, at the anode, oxidation takes place and it produces chlorine gas. Cl2 gas is a diatomic gas. 2Cl minus gives you Cl2 plus 2 electron, loss of electrons, oxidation reaction. So those are the products of electrolysis of molten sodium chloride. Now if you take any ionic compound and if you electrolyze in its molten state, you will get the metal at the cathode and the non-metal at the anode. Oxidation and reduction of water. So when we are going to look at the electrolysis of ionic compounds in water, we also have to see what would happen to water if you pass electrical energy into it. So whenever we are looking at electrolysis of ionic compounds in water, we will look at the tendency of the positive and negative ions to be undergoing reduction and oxidation. At the same time, water, is it being impacted by the process of oxidation and reduction? That's what we're really going to look at. So let's look at the two possibilities here. Reduction of water. Water can be reduced. In that case, it will gain 2 moles of electrons and changes into hydrogen gas and hydroxide ions. The standard reduction potential for the reduction of water is minus 0.83 volts. So if you refer to the standard reduction potential chart that is given to you, you would find this value and you will see the reaction is a reduction reaction. So every time water undergoes reduction, it produces hydrogen gas. And the solution surrounding the cathode, which is where the reduction takes place, becomes rich in hydroxide ions. Therefore, the pH of the solution around the cathode will increase. And we can actually detect it by using an indicator, and we can see the change, color change happening with the increasing concentration of hydroxide ions. Now, if we compare the standard reduction potentials of water with the metal ions that is present in water, the one with higher standard reduction potential is reduced. So we're going to look for competition. So there are two substances that are present in water. The positive ion which likes to be reduced, and there is water which likes to be reduced. And if you look at the standard reduction potential of the metal, if that has got a higher standard reduction potential value, then that metal will be reduced. If that's not the case, water will be reduced. When water is reduced, hydrogen is produced at the cathode. If, on the other hand, water has a lower reduction potential value, then the metal will undergo reduction. So that should be very clear in your mind. Every time you are having an aqueous solution, you're going to compare the standard reduction potentials of the positive ions and water. Whichever has a higher standard reduction potential value will undergo reduction. And based on that, the products change at the cathode. Similarly, we're going to look at oxidation of water. Oxidation takes place at the anode. So water can be oxidized to give you oxygen and 4H positive. which means along with the production of oxygen at the anode, it also produces hydrogen ions, which makes the solution acidic, and therefore the pH of the solution will go down. And the standard reduction potential for water is 1.23 volt. Now, while we are using standard reduction potentials, if you want to predict the tendency for oxidation and reduction in an electrolytic cell, I would use the standard oxidation potential for water at the anode. So in this case, if I look at the standard oxidation potential for water, it's going to be minus 1.23 volts. Change the sign of the standard reduction potential value and you will get the standard oxidation potential. Again, we will speak with reference to the reduction potential first. If water has a lower reduction potential than the anion present in the solution, then water will be oxidized in comparison to the anion and oxygen will be produced at the anode. Now, if you look at the standard oxidation potential, the standard oxidation potential of water is minus 1.23 volt. The reduction potential value is 1.23 volt, but if you want to use standard oxidation potential, change the sign, the opposite reaction. So alternatively using standard oxidation potential, and if water has a higher standard oxidation potential than the anion, then it will undergo oxidation. So we're going to compare the two ions. One is the anion that is present in the solution and water. And if you look at the standard oxidation potential, the one with a higher standard oxidation potential will undergo oxidation. That's the basis for predicting the products that may be obtained whenever an aqueous solution of an ionic compound is undergoing electrolysis. So that's a general statement that we have made. Water can undergo oxidation and water can undergo reduction. If water undergoes oxidation, it produces oxygen and the solution becomes acidic. If water undergoes reduction, it produces hydrogen and the solution becomes basic. These are two things that we have used, and we have also stated that in order to predict which electrode or which ion undergoes oxidation or reduction, we can use standard reduction potentials for the cathode and standard oxidation potentials for the anode. It becomes easier to make the prediction. So, electrolysis of an aqueous sodium chloride solution. Here is a graphical representation of an electrolytic cell. We have platinum electrodes in an electrolytic cell. We have sodium chloride dissolved in water. So inside this container, we have two different types of ions and water. Anode, which is the positive electrode. Cathode, which is the negative electrode. The reactions obviously is oxidation at the anode and reduction at the cathode. Now here are the three reactants that we have. Sodium ions, the standard reduction potential is minus 2.71 volt. And water, the standard reduction potential value is minus 0.83 volt. So we're looking at the tendency for reduction. So between the two, sodium ions and water, water has a larger standard reduction potential value. Therefore, water will be reduced in comparison to sodium. So at the cathode, where reduction takes place, water will be reduced, and when water is reduced, it produces hydrogen gas. And if you compare what would happen at the anode, where oxidation should take place, the chloride ions should react, or water can react with the electrode and undergo oxidation. So if you compare the standard oxidation potential, Cl minus is minus 1.36 volts and water is minus 1.23 volts. So ideally, the one with a larger oxidation potential tends to undergo oxidation. So we expect water to undergo oxidation in this case. But the reality is, when you perform electrolysis of sodium chloride in water, normally we do not get oxygen at the anode. Instead, we will get chlorine gas. So this is an exception and there are reasons for it. We will discuss the reason for it in the next slide. So the reaction that is taking place at the anode is 2Cl minus gives you Cl2 plus 2 electrons. And the standard reduction potential value is 1.36 volt. Here water is undergoing reduction and the value is minus 0.83 volt. We have two reactions, the oxidation half reaction and the reduction half reaction, which should be able to tell us what the net cell reaction is. Now we are going to explain why this is an exception and you may want to do some additional reading. So let's go to the next slide. It would appear easier to oxidize water than chloride ions, which we have already stated, because water has a higher standard oxidation potential. The solutions which we electrolyze normally has a 25% sodium chloride by mass, therefore, which significantly decreases the potential required to oxidize the Cl-. The pH of the cell is also kept very high, which decreases the oxidation potential for water. The deciding factor is also known as the overvoltage, which is the extra voltage that must be applied to the reaction to get it to occur at a rate at which it would occur in an ideal system. Therefore, there are three statements or three facts that we have put here. One is the concentration of sodium chloride is pretty high, the pH of the solution is pretty high, and then we are talking about overvoltage. Do some additional reading on what overvoltage is. That will give you an idea. So this causes a change in the final product during the electrolysis of aqueous solution of sodium chloride in water. The products obtained at the anode during electrolysis for this reason is chlorine gas, and we have already stated the reason: high concentration of NaCl, high pH, and over voltage. And at the cathode we would get hydrogen, because hydrogen has got a larger reduction potential value than sodium. Now, generalizing, whenever we have reactions taking place in an electrolytic cell where the salts dissolved contain sulfate ions and nitrate ions, this is an observation that we have made. It's difficult to oxidize sulfate ions and nitrate ions. These polyatomic ions are pretty stable and strong, and therefore they do not decompose easily to change into other compounds under the potential difference that is being applied in the electrolytic cell. For that reason, under normal circumstances, sulfate ions and nitrate ions do not undergo oxidation. If you keep this in mind, it becomes reasonable to explain why and what the products may be at the different electrodes or at the anode in an electrolytic cell involving aqueous solutions of ionic compounds. These ions do not oxidize at the anode for the reactions that we will be discussing. Hence, OH- ions will be discharged or oxygen will be produced at the anode. So that's the generalization that I'm going to use here to predict the products that are obtained in the next electrolysis. Again, looking at the representation of the electrolytic cell, we have the anode, we have the cathode, we have reduction. Here, water is undergoing reduction because water has got a higher standard reduction potential than potassium, and therefore hydrogen is produced and the solution becomes basic around the cathode. Oxidation takes place at the anode, and again, in this case, nitrates are present in the solution. That's difficult to undergo oxidation. Therefore, water preferentially undergoes oxidation, producing oxygen gas and hydrogen ions, making the solution more acidic or the pH drops. So if you electrolyze potassium nitrate, you can actually produce oxygen and hydrogen. Now, you may have also seen that in grade 9 and grade 10 using the Hoffman's apparatus that you would have produced oxygen and hydrogen by the decomposition of water using dilute sulfuric acid. Same thing happens there. Sulfuric acid contains sulfate ions. Similarly, potassium nitrate contains nitrate ions, which is difficult to oxidize and therefore produces oxygen because water is easier to oxidize in these cases. So we have seen three cases of electrolysis: molten NaCl, aqueous NaCl, and aqueous potassium nitrate. Three cases where the products are different, and some exceptions when we are looking at aqueous sodium chloride, and we had seen the reasons for those exceptions too. So it is an expectation that you should be able to explain using oxidation half reaction, reduction half reaction. And you can also calculate the cell potential using E0 cell is equals to E0 cathode minus anode, and then predict the value of E0 cell, which should be negative in all of these cases because the reaction is non-spontaneous. So electrolysis of potassium nitrate, water undergoes oxidation at the anode, water undergoes reduction at the cathode. So electrolysis of potassium nitrate produces oxygen and hydrogen at the anode and cathode. Therefore, to generalize, at cathode the metal is formed if metal is below hydrogen in the standard reduction potential value, and if not, hydrogen is produced due to reduction. At the anode, usually you get oxygen if nitrate or sulfate ions are present as anions. If the negative ions are chloride, bromide, and iodide, it usually produces chlorine gas, bromine gas, and iodine. Depending on electrodes also, the products formed can change. Sometimes we can use carbon as the electrode, but in the cases that we have discussed, we have used platinum as the electrode. Now, here are some applications of electrolytic cells. Industrially, there is a lot of applications, and we are taking the benefits of many of these electrolytic reduction that is taking place, especially industrially. So we're going to look at some generalizations and statements about where this is being applied. We're not discussing in detail how those processes work. I would suggest do some reading on it. Preparing highly reactive metals by electrolytic reduction. So aluminum and sodium, they can be prepared using electrolytic reduction. Sodium is a highly reactive metal, and in order to prepare that, electrolytic reduction is a very good method, because if you do not expend energy, you cannot reduce sodium ions to sodium atom. So it's a non-spontaneous reaction. We have to use energy. Same is the case with aluminum. Aluminum is, if exposed to nature, easily undergoes oxidation. So for those reasons, preparing aluminum and sodium, and there are methods adopted with industrially to prepare these metals. So it's a good idea to do some reading on the industrial production of aluminum and sodium and the methods adopted, type of electrolytic cells used. These are modified versions so that we can obtain products that we desire. Now, purification of metals like copper is also done using a process called electrolytic reduction. The chemical process produces copper which is only 96% pure, and to increase the copper content, we actually use electrolytic reduction. And when we perform electrolytic reduction, the quality of copper is almost 99.9% is copper, pure copper. So for that reason, electrolytic reduction is an important aspect industrially which adopts electrolytic reduction or electrolytic cells. Another important application of electrolytic cell is plating of base metals. The chrome-plated bikes like Harley-Davidson or gold-plated ornaments or silver-plated ornaments are usually done using electrolytic cells. The base metal that is to be coated with a shiny metal like chromium or gold or silver is usually the cathode. At the cathode, there is reduction taking place. Therefore, the metal that is going to be deposited actually deposits on the cathode. So the anode is usually made the metal that is going to coat the cathode, and the solution, the aqueous solution that we use, will contain those same ions. So reading about plating, electrolytic reduction, and preparation of highly reactive metals are some applications of electrolytic reduction, and that is an area that you would be working by yourself. So make sure you do some reading in that area. We're going to do some calculations involving electrolytic reduction. In order to do that, we will need to recall some of the equations that we may have learned in grade 9, and also look at some general concepts for determining the number of moles of electrons that are flowing through a circuit. So we are going to predict the mass of substances that are produced at the anode and the cathode. Some terms that you are already familiar with. I represents the ampere or the current strength. 1 ampere is 1 coulomb per second. If you have 5 amp current, it means 5 coulombs are flowing through a circuit per second. Or 2.5 amperes would mean 2.5 coulombs per second. So ampere represents the current strength, represented by the letter I. Q is equals to I times T, which means Q is representing the total charge in a circuit. We can calculate that. by multiplying the current strength in amperes by the time taken. Coulombs per second times second will give you coulombs. So that's the total charge. Always time is calculated in seconds because the unit of ampere is coulombs per second. Or we can use this information to calculate the number of moles of electrons that are flowing through a circuit. So in this case, Ne would represent the number of moles of electrons. And how do you calculate the number of moles of electrons? If you have the total charge that is flowing through a circuit and divided by the charge of 1 mole of electrons, you would get the number of moles of electrons. And Ne would give us the number of moles of electrons. We will calculate that by dividing the total charge, which is IT, by F. F is called Faraday's constant. Faraday's constant is a charge carried by 1 mole of electrons. So the total charge divided by the charge of 1 mole of electron will give you the number of moles of electrons flowing through the circuit. So this is an equation you may want to recall. Ne is equals to IT by F. That equation is something that you're going to learn and memorize to do the calculations. Voltage is a measure of the amount of energy that can be delivered by a coulomb of electrical charge. So we're talking about electromotive force or EMF or voltage, and 1 volt is given as 1 joule per coulomb. So we're going to use Faraday's laws to do the calculation, even though we don't have to specify it as Faraday's law, but you can reason it out using the method that we have stated earlier. By calculating the number of moles of electrons in a circuit, we can predict the amount of substance that is precipitated or deposited at the cathode or liberated at the anode. If you want to say the statement, the amount of chemical change that occurs during electrolysis is directly proportional to the amount of current that is passed through the electrolytic cell. Faraday's constant. The charge carried by 1 mole of electron is called a Faraday. 1 Faraday is equals to Avogadro's number times charge of an electron. Avogadro's number is 6.022 into 10 to the power of 23. And the charge of an electron is 1.6 into 10 to the power of negative 19 coulombs. So 1 Faraday is equals to 96,485 coulombs. Here is a problem for you. A current of 5 ampere is passed through melted KCl for 1000 seconds. How many grams of potassium are produced? So here you have a current strength I of 5 amperes, which means 5 coulombs per second, is passed through molten potassium chloride, which means we only have potassium ions and chloride ions, and the time for which the current is passed is 1000 seconds. So now we have to write a chemical equation for the reaction that is taking place at the cathode, which is reduction, and then we have to calculate the number of moles of electrons that are actually flowing through the circuit. Once you have the number of moles of electrons, you can calculate the number of moles of potassium ions that are actually reduced. That's what we're going to do here. So if you use electrolysis to produce potassium, the reaction would take place at the cathode, where we will see a reduction reaction taking place, which can be represented as follows. So this is the reaction taking place at the cathode. K positive plus electron gives you K. Ionic potassium changes into atomic potassium and it exists as a solid. Since K is monoatomic, the number of moles of potassium produced at the cathode is equal to the number of moles of electrons consumed, or the number of moles of electrons flowing through the circuit for 1000 seconds. So this is how we can calculate it. Number of moles of electron is equals to total charge by charge of 1 mole of electrons. So IT by F. I is the current strength in ampere, is 5.0 amperes. Time is 1000 seconds. And Faraday's constant is 96,500 coulombs. I've used the rounded off value for Faraday's constant. And when you substitute these numbers, Ne is equals to 5 coulombs per second times 1000 second divided by 96,500 coulombs will give you 0.0518 moles of electrons. So the number of moles of electrons that are flowing through the circuit, we have And if you have a balanced equation, we can find out the number of moles of potassium. Or we can say 0.0518 moles of potassium ions will need 0.0518 moles of electrons, and it will produce 0.0518 moles of K. So this is exactly the same equation that we have written in the previous slide. Now we are using a value for the number of moles of potassium we have based on the calculation used above, which means we have 0.0518 moles of potassium. Next thing to do would be to convert moles to grams, and for that we can use the equation N is equals to M over molar mass, or M is equals to N times molar mass, which is 0.0518 moles of potassium times 39.0978 grams per mole of potassium, which will give you 2.025 grams of potassium. Here is a second problem for you. How many grams of chlorine gas would be produced in the electrolysis of sodium chloride by a current of 2.50 amperes for 40 minutes? So here we are trying to produce chlorine gas by the electrolysis of sodium chloride. So here we know that the current strength is 2.5 amperes or 2.50 coulombs per second. And we have the time for which the current is passed, which is 40 minutes. We have to convert that to seconds. 1 minute is 60 seconds. Using that conversion factor, you can actually convert minutes into seconds. Chlorine is an anion, therefore it goes towards the anode, where it gives up its electron and changes into chlorine gas. So the reaction that represents the reaction at anode is 2Cl minus gives you Cl2 plus 2 electrons. So first we will calculate the total charge in the circuit. Ne is equal to IT by F. Ne is equal to I is 2.5 coulombs per second times 40 minutes into 60 seconds per minute divided by 96,500 coulombs per second. This will give you 0.0622 moles of electrons, or 2Cl minus gives you Cl2 plus 2 electrons. 1 mole of chlorine gas will produce 2 moles of electrons, or 1 mole of chlorine gas requires 2 moles of electrons. Or we can say the number of moles of chlorine Cl2 is equals to number of moles of electrons divided by 2, which is 0.0311 moles of chlorine gas. And you can convert the number of moles of chlorine gas to grams using the equation N is equals to M over mm, or M is equals to 0.0311 moles into 70.9 grams per mole. 70.9 is the molar mass of 1 mole of chlorine gas or diatomic chlorine gas, which is equals to 2.205 grams of chlorine. So that's how you can calculate the amount of substance that is liberated at the anode or deposited at the cathode by calculating the number of moles of electrons that are actually flowing through the circuit. Those are the two different calculations which you will be seeing with different examples though. So that's a summary of electrolytic cells.